Syzygy, episode 34. This system's got everything. Welcome to episode 34 of the Syzygy podcast. Sitting opposite me at the table, Emily Brunsden. Hi, Emily.
Hello, hello.
So what's going on this week? We've got, we on this podcast, we talk quite a lot about one of our favorite topics, which is the exoplanets, the planets that we found around other stars. And we're going to be talking about that again today because we've reached a milestone. There's a big milestone happening. What's going on?
Well, we are so close, super close to being able to say that we have discovered 4,000 exoplanets.
4,000. The big 4K. That's a lot of exoplanets. But doesn't it kind of depend on how you count them? I mean, I like we've reached 4,000 or we haven't reached 4,000. Some people think we've reached 4,000.
Yeah. So the number that I'm using at the moment is the number come from the Exoplanet Archive, which is NASA's archive that they run.
So NASA has said we're almost there, folks. You can watch it tick over to the 4,000.
Yep. So on the NASA Exoplanets Archive, we currently have 3,926.
Now, are you one of those sorts of people? Do you have a car?
Yes.
Do you watch when the numbers tick around on the odometer on your car? It's like, oh, we're almost at 4,000. And because I'm that person in my family, and everyone else, like my wife and kids, just go, "That's great, Dad. Good on you." When I say, look, it's exciting. We've just reached 20,000 miles. Look, happy birthday, car. And they just don't care. Do you care about that sort of thing?
So I have to pull over to the side of the road and take a photo of the odometer at that point.
Okay, good. So we're on the same page on that one. In which case, you and I are both very much on the same page of it's just a number, but it's a good number. 4,000 exoplanets. That's awesome.
It's really amazing. And it could be that we tick over this just in the next few days because sometimes these exoplanet discoveries come in bursts, right?
Yeah. And this isn't just, these aren't ticking over sort of, oh, look, we just saw another exoplanet, mark that up by another one. There are a whole bunch of candidates, aren't there, sort of in waiting to be verified. So there's like, a couple of thousand exoplanets sitting there in the, not sure, that might be an exoplanet and it needs further checking. Is that right?
Yeah, and this is kind of why we have differences between the numbers. So some of the archives are already reporting over 4,000 exoplanets.
Right.
And it kind of depends a little bit on how you count. Because what we're talking about here with this number is confirmed exoplanets. So that means that either we've seen many instances of the same event, if that's a transit or a period from the radial velocities of the planet.
Right, so it's not just one blip. Oh, that could be the right kind of blip that means an exoplanet. We've seen that a few times. That's definitely an exoplanet.
Yeah, and we've seen it with different instruments within the original one that discovered it, or we've seen it with a different technique altogether and confirmed that those exoplanets are there.
Cool. So some people have said, yep, we've definitely confirmed a few more of these exoplanets and we're over 4,000. And NASA is saying, no, we're not quite there yet, but we're almost there.
Almost there. And it also depends on where you draw the line between what's a planet and what's a sort of small failed star.
Ah, okay. So very, very large gaseous planet or very, very small failed star. It's iffy. It's a grey zone.
Once you get to around 13 times the mass of Jupiter, it becomes, are you a planet? Are you a star?
Yeah, fair enough.
Not really sure.
Fair enough. Yeah. And there are a few of those in the mix.
Yeah, there are. Yeah.
Okay. Well, regardless, if you're a fan of exoplanets and if you're a fan of numbers, round numbers, nice round numbers with zeros in them, then this is a good week.
It is. And I can tell you some more numbers.
Go on then.
Since you're a fan of numbers,
Come
I
on.
know you are. So of those 3,926, now this is something that, of course, is a huge credit to NASA. The Kepler mission, which is this Kepler's Space Telescope. We've talked about it many, many times.
Yeah.
We love Kepler.
And Kepler, the mission actually came to an end, when? Was it?
Late last year.
Late last year.
Yeah.
So just recently.
So Kepler found so far 2,338 confirmed exoplanets.
That's a lot.
It's about 60% of all the ones that we know.
Yeah. With thousands more waiting in the wings.
Thousands more, 2,400 more waiting to be confirmed
it
from
alone
Kepler.
Could be over the 4,000.
Yeah, definitely. Yeah. And then we've got TESS,
Yay!
of course, as well. So TESS is doing well. TESS has got 8 confirmed planets.
It's on its way.
Yeah.
But many more
Yeah,
unconfirmed.
471.
So
still
8
to
doesn't
confirm.
sound like a big number, but it's making lots of observations. It's just that we, meaty humans, haven't caught up with the confirmations yet.
Yeah, and be aware we've only had our hands on the data since December,
Yeah.
and that's only been a part of the
So
data.
that's pretty good.
Yeah, this is really brand new stuff, and we expect that number to increase pretty dramatically over the next few months.
Excellent. Good stuff. All right. So that's the sort of number-based exoplanet news this week. But there's been some other exoplanet news this week, including, it's another milestone, the first exoplanet which we've actually kind of seen directly.
Directly through optical interferometry.
Okay,
So,
so-
you've got to put those sort of categories.
So
in
there are
there.
caveats here.
Yeah,
All right. So let's talk us through this one. First of all, what's the research? Who and where?
Okay, so we're looking at a team from the European Southern Observatory, ESO, not ESA. It's very
Different group.
close. Yeah, ESO, the European Southern Observatory. And they've got
That's the one in Chile?
It's the one in Chile, yeah. And they've got a lovely instrument on the VLT in Chile called Gravity.
Mm-hmm.
And Gravity is run by the Max Planck Institute.
Right. And the VLT is the very large telescope.
It is.
As opposed to the excessively large telescope and the annoyingly large telescope.
The overwhelmingly
and
large
the
telescope.
stupidly large telescope.
The Final Death telescope.
Yeah, that's right. The one that's so big it just implodes as a black hole and kills us all. Anyway, so the VLT, and they've got this instrument called Gravity, which does what?
Well, actually, we've talked about Gravity before.
We have actually, back, what was it, episode 16?
Episode 16.
Yep.
And do you remember what that episode was about?
No. It's too long ago. We talked about too much.
We were talking about a star that was hurtling around a black hole in the center of our galaxy.
That's right. That's right. We were, weren't we?
Yeah. And so in that particular episode, we talked a lot about how we use this instrument to be able to peer through all the dust and stars and all the sort of rubbish that's in between us and the center of the galaxy.
Right, because it turns out looking to the center of the galaxy is actually really hard because there's a lot of stuff between us and the center of the galaxy.
A lot of stuff in the way. So what they were doing was this interferometry technique, which means that you're combining the light from up to 4 telescopes. And these aren't, tiddly little telescopes you take out onto your lawn.
No.
These are 8.2 meter diameter mirror telescopes.
Which is big by anyone's
Big.
estimate.
Yeah,
That's
some of
a
the
big
largest
telescope.
telescopes in the
Yeah.
world.
And not just one, but 4 of them.
4 of them.
Combining it all together and comparing that data to see incredibly subtle differences and coincidences between them in order to basically turn it into one huge telescope.
Yeah. So light's a wave, and then when you combine the waves coming in from the 4 instruments very, very cleverly, then you can actually get them to all add up to one enormous telescope together, which is so, so cool. And when we talked about this in episode 16, they were using this in the infrared part of the spectrum. So that means that we could see through all the gas and dust and stars that were in the way.
Right, because the visible gets blocked by all that gas, but the infrared gets through.
Yes. Yeah. So we're definitely doing those observations in the infrared to see to the center. And doing this interferometry in the infrared, we've been pretty good at doing that for quite a number of years now. Because infrared light is quite long wavelengths compared to the light that we see with our eyes. So if you recall back to the electromagnetic spectrum, you've got the visible light that we see, which is a few hundred nanometers. You go to infrared, it starts to get longer. You get down to sort of millimeters, then you get into centimeters, and finally you get into radio waves, which are kind of meters in length. So we started off with all this technology way back by doing it with radio waves because it was quite easy to combine something that's a meter long with something that's a meter long and get it to match up, right?
Right. Yeah. It's easier to sort of line those rulers up in a sense. Yeah.
And this is used across radio telescopes across the world, and it's extensively used radio interferometry. Even the new SKA instrument is kind of going to be the largest example we're going to have of this.
Yeah, I mean, that's radio dishes, radio antennas in huge numbers spread across Australia
Thousands.
and Africa and some in New Zealand as well, I think.
Yep.
But just over this enormous distance, and all of it being correlated together to create this stupidly big virtual telescope. Yeah, but that's with radio.
Yeah.
And so because the wavelengths are much longer, that's a much easier, although still very much non-trivial, problem. Whereas we're talking about infrared.
Yeah, so the smaller the wavelength that you get, the harder it becomes.
Right. So that's pretty tricky.
Yeah, so infrared is already quite hard, although we have been able to do this for a few decades now. But now we're talking about doing this in the optical. So we're
Which
going
is
to
even harder.
smaller wavelengths.
Yeah, so these are a fraction of the wavelength of the infrared.
Yeah.
And we're getting down into, as you say, hundreds of nanometers.
Yes.
Yeah, fractions of a micron.
Yes. So basically hair widths and
Yeah.
less, right?
Yeah, tiny.
So you've got to try and combine those waves together such that they all line up and match up. And that's very, very difficult. So we have been able to do optical interferometry before. Keck was a really famous example. So that's a huge
that's
telescope
right.
in Hawaii.
Yeah.
They gave up their optical interferometry program some time ago, but it's been reinstated since. So I think they're still working on redeveloping that technology. But Gravity has also been working on getting this technology even better. And they're doing a fantastic, fantastic job.
Yeah, because in this case, they've used... So is it still using all four of the telescopes, the 8-meter telescopes?
It's using two or more.
Two or more.
Yeah, it depends on, I guess, each observation, how many they choose to use.
But in this particular case, looking in the optical, and they've, for the first time, using optical interferometry, they've spotted an exoplanet. And this is not, hey, there was a blip in the light coming out from a star that showed that it was in transit. This is actually seeing
this is
the
a
planet.
real imaging detection.
This is seeing it.
Yes.
A very, very long way away around a completely different star.
Yes.
Which just blows my mind.
Now, I'm going to calm you down a little bit here.
Okay.
Because we did know that exoplanet was there.
Right. Okay. So that makes it a bit easier.
So we did know where to look.
Even so.
And it's also not the first image that we have of this exoplanet.
Okay, all right. So how was the image taken before then?
So what we actually, going back to Keck, when we think about the system when it was discovered, starting from 2008, they discovered the first 3 exoplanets around the system, and then in 2010 confirmed the 4th, which is the one that VLT has just been looking at. And they were able to use infrared technology to image directly these exoplanets. And it's very unusual that you can do this, right? Because exoplanets, first of all, are tiny.
Well, yeah.
Right.
Yeah. Even the big ones.
Even
the big ones are
Even
tiny.
the big ones are really, really
and
small.
they're a really long way away. Like, this isn't like looking at... Like, Jupiter's small in the night sky.
Yeah.
Right? It's tiny, but that's huge by comparison. We're talking about completely different stars with planets around them. That's minute. So...
And importantly, they're not bright.
Yeah.
Right? They don't shine like a star shines.
No, they're reflecting light, if anything.
Yeah. And so they're very, very difficult to spot, to take photographs of. So we have very, very few exoplanets that we've been able to take images of.
Right. But Keck was doing it in the infrared.
Yes.
Okay.
And the reason why you can do it in the infrared for these exoplanets is actually because they're very, very young.
Okay.
And this is
Talk me through that.
This is quite cool. So the star itself is very, very young. So we're talking about only maybe 30 to 100 million years old.
Which is young for a star.
It's very, very young.
Yeah.
So consider our sun, which is maybe 4.5 billion, 5 billion years old.
Okay, and you're talking in the millions.
And yeah, we're talking only a few tens of millions.
Yeah.
So really, really young star, which means everything's formed very, very recently. So to give you an idea of the scale of this system, if you took our solar system and you took our planets, Jupiter, Saturn, Uranus, and Neptune, 4 exoplanets or 4 planets. The 4 exoplanets we have are similar to these exoplanets if you multiply the distances from the star by 2.
Right, so they're all big planets and further away.
Yeah, so they're kind of double the size, the scale of our solar system. So
Okay.
they're quite far away from their host star, which is why we're able to image them as well, because we're able to use kind of basically just a shield to block out the light from the host star.
I see. So if you put sort of a bit of a mask in the way as you're looking at these things, blocking out the light from the star itself and looking at what's left over, then you're blocking out that really bright bit, but you're still letting the light through that might be, for example, bouncing off these bloody great planets sitting out there going around it. Is that the idea?
Yeah. So basically, it's like when you hold up your hand to block out the light from the sun, right?
Yeah.
It's
That's a
not
much
really,
better analogy. Yeah.
It's not really any more complicated than
Yeah.
that. You're just reducing the glare by taking away that extra light that's from the star. And what you can do then is you've taken away all the glare, is you see not the light actually that's reflected from the star onto the planets, but you see the light that the planets themselves are emitting because they're warm.
Right, and you were saying because they're so new.
Because they're new.
They're still cooling down.
Yeah. So that means that these exoplanets are kind of 1,000 degrees or
Right.
so.
Right. So that makes sense that you would then be able to see them in the infrared, because that's a bit easier to do with the interferometry. But if you're sort of looking at the heat that's coming from them, then that kind of makes sense. These are the same planets that they're now imaging optically.
Yes, yeah. Well, they've just done the one planet with the optical interferometry so far. Yeah, so these four exoplanets are in the system, and we were talking about exoplanet E. So its full glorious name is HR 8799E.
Always well named. And now, hang on, if I remember correctly, you don't start with A, because we don't start with A when we're talking about planets.
There's no A's.
B, C, D, E. This is the fourth.
It's the fourth discovered.
Yes, not fourth in order out.
It's the closest one to the star.
Right. Okay.
Yeah. Just because. Just because.
Anyway, moving on.
So exoplanet. So this one, it's about. So it's to say twice the distance as Jupiter is from our sun. From its host
twice
star.
The size, did you say?
Well, about 7 times
right.
the size of Jupiter.
So big thing.
So it's a big
thing, far away, and still glowing a bit.
Still glowing a bit. Interestingly, because the star is hotter than our sun, even though it's twice as far away, it still gets about the same amount of radiation from that host star. So it's quite an interesting little exoplanet. And what they've been able to do is take all the light from this interferometry, optical interferometry, and put it through a spectrograph and look at what is the atmosphere of this exoplanet composed of.
So what's a spectrograph?
So a spectrograph takes the light that we're looking at and breaks it up into all the different constituent colors or wavelengths, kind of a fancy version of a prism.
Yeah, like you put light through a prism, or through a raindrop, and it splits apart into its colors. If you do that for light across all its wavelengths, you can see much more than just the red, orange, yellow, green, blue, indigo, and violet. You could see all of the different colors. But importantly, you can see specific bits of that spectrum that tell you information about what's there, what's on the planet, what's in the planet.
Yeah, because every element in the periodic table has its own fingerprint, its own signature that it has in a spectrum. And we can use that, therefore, to say, well, in the spectrum, we can see the fingerprints of, in this exoplanet's case, iron and silicates.
And that spectrum, those fingerprints are showing that that's in the atmosphere?
That's in the atmosphere, yeah. And from looking at how you can get these ions and silicates to be in the abundances that they are in the atmosphere, we can now say that this exoplanet has a global storm that's swirling up all this, because iron and silicates are quite heavy materials, right? Okay,
so you'd expect them on, a huge gassy planet. You'd expect them to sort of settle down and be dragged down towards the middle of the planet.
Very slowly those particles kind of sink down.
Like heavy stuff settling out of a mixture of water and grit. All the heavy stuff would settle down to the bottom, unless there's a bloody great storm swirling around on the surface, mixing it all up.
And the storm is the size of the planet.
So how do they know that?
That's crazy.
How do they know that?
I think you need to have the energies involved, that you need to have this mixing, and then you look at the convection. And it's really, really fascinating.
I love the fact that astronomers and planetary astronomers can take what seems to the outside world like, hang on, you've just made like a couple of measurements and you've come up with huge 7 times the size of Jupiter, global-sized storm. Like, where does that come from? It's like, well, if you look at the energy and you figure this out and you put that in and you understand that about where that's all got to come from, then you get big storm. I love that. That's brilliant.
It's really, really amazing, isn't it? So it's very, very interesting exoplanet. It's not going to be somewhere we're going to want to live.
Doesn't sound it.
No.
I mean, Jupiter's not going to be a nice place to try to land on. So something much bigger than that, a long way away with a global-sized storm on it, doesn't really... But it's cool.
It is very, very cool. Now, I don't know if you knew this, but you flicked this article to me and said, hey, Millie, we should do a podcast on this. This is quite cool.
Yeah, I'll take that. I'll take that blame.
Yep.
I'll take that credit.
And I read through the article and I was like, oh yeah, this is quite interesting. Interferometry is cool. The new technique used to discover or to confirm the existence of an exoplanet. This is very cool. And then I looked at it again. I looked at the star and I was like, this star, HR 8799. Why does that
ringing any bells
sound
with
familiar? Me. It definitely sounded familiar to me. And then I suddenly thought, I know what this star is.
Uh-oh.
This is not just any old star.
Uh-oh.
gonna overwhelm you with excitement here.
Okay, I'm ready. I'm clutching the table here. I'm ready.
This star is a Gamma Dorada star.
Oh my God! Now just remind us what that means.
That means it's one of the very few stars that I'm actually super researchy interested in.
What are the odds? What are the odds? So remind us again. Gamma Dorada.
So
is
Gamma
what?
Dorada stars are the type of stars that I really kind of spend the majority of my research drilling and down into, and very
This is
intricate
your thing.
and, yeah, very fine detail.
So no wonder that rang a bell. But what is a Gamma Dorada
So
star?
the type of pulsating star.
Right.
So that means the star has pulsations across the entire surface. And those pulsations kind of are what we call non-radial, which means you get parts of the star moving in, parts of the star moving out.
So it's doing this sort of big kind of resonant wobble.
Yeah. Big pulsation. It's like a big wave traveling around the surface.
Right.
And you get different nodes and different lumps and bumps all over the surface.
And we've talked about that briefly before, but not in a lot of detail. What causes that?
So it's based on the kind of the conditions in really deep inside the star itself. You get to a particular set of temperatures and pressures where stars are kind of inherently unstable. They can't get their energy out fast enough and so you get a build-up of energy on the inside of the star, and that has to be released. And the way you release it is by expanding, having a pulsation move through the star.
And it's doing that, periodically? Is that why it's sort of setting up these waves?
Yep. So it has lovely periods, so you can just see it pulse in and out and in and out and in and out. In the case of this star, we're looking at nearly exactly 2 pulsations every day. So that means one cycle takes about half a day, 12 hours. It was amazing that, because I think I don't normally deal in HR numbers. This is a catalogue that I tend to not use so much, but I did happen to remember this one because actually I think it's the only Gamma Dorada star that we have confirmed exoplanets around, or at least one that we've studied in this kind of detail.
Wow. So this is doubly exciting for you this week.
Yeah, I mean, so
you're all over this one.
If you consider maybe there's 100 Gamma Dorada stars that I look at from the ground, and this is one of them, then it was pretty amazing.
I mean, I guess statistically on this podcast, we were going to do this eventually. Something was going to come up that you were going to go, hang on, wait a minute. But, who'd have thought that it would happen in episode 34? Statistically, we might have had to wait hundreds of podcasts for that to happen. But no, here we are.
Yeah. And I remember this because so when I did my PhD, you sort of become one of a generation of PhD students, right? And if I think about the generation before me, so the guy who did the PhD before me is a guy named Duncan. And he did a fantastic job. He was using the same instrument, developed a lot of the techniques that I ended up using in my own thesis. And so we worked together for a couple of years. And not long after he finished his PhD, he worked on this star. And he used data from the same instrument in New Zealand that I used. And he studied the pulsations to try and understand what was going on. We knew that there were some planets around this star. So we thought that there was going to be an interesting question. Because when you have pulsations in a star and you observe them using spectroscopy, the techniques that I use, then you can actually say something quite often about how the star is inclined to your line of sight.
Okay.
So what that means is so if you imagine it's got an axis that the star rotates, it means is the axis tilted towards you, so you just see the North Pole of the star?
You're just seeing it spinning around end on.
Or is that at 90 degrees, which means you see the equator and you see basically the whole surface area of the star? Or is it any angle in between? Right?
Sure.
And that's an interesting question because now we've got planets and we want to know, is the way that the angle that the planets are going around this host star the same as the angle that the star is rotating?
Is it true that most of the time, all of the time, planets end up going around the star in the same direction that the star is rotating, like all in the same plane, because they've all come from the same origins?
Yeah, and that's true in our solar system,
Yeah.
right? The sun rotates. It rotates. The equator of the sun, if you like, is aligned to the plane that all the planets orbit the sun.
Because they all came from the same rotating big blob of gas in the first place. And so that original rotation is what's left over when everything's collapsed down. Everything ends up rotating in pretty much the same way, give or take a little bit.
Yeah, but the give or take is actually really, really little, especially in our solar system. It's tiny.
So you would expect that this other star, this Gamma Dorada star, and all of its planets ought to be rotating similarly in a plane.
Yeah,
Right.
but they're not.
Okay.
Which was which was really, really exciting. So this is what Duncan discovered. He used the data that we were on the pulsations, and he was able to work out the angle, which was the star's rotation axis from the pulsations. And he found out that it has to be more than about 40 degrees. So this means that you have kind of a relatively well tilted to your line of sight. And that makes sense to us as pulsation people, because if you just look at the pole of a star, actually it's very difficult to discern if there's pulsations there or not. You don't expect to be able to see them very easily.
Right, okay. But if you're looking at it side on, it's much more obvious.
It's much more obvious,
okay.
Yeah. And so, it's going to be more than 40 degrees based on the models that we have and the understanding of the pulsations we have. The planets are going around at an angle of 10 degrees.
Well, that's a big difference. Like, if I remember geometry at all, then 40 degrees is not 10 degrees. It's about 30 degrees off.
Yeah, so we can approximate this. So imagine you're looking at the sky and looking at the system, and you can actually see the planets. Mm-hmm. Then you're looking at the star in the middle and the planets going around, and they are going around the star in the same plane. So you can see the whole orbit of all the planets,
yeah.
right? They're going around in a circle, just a big circle that's a bit bigger than the star itself.
Sure.
Now, the star itself is angled so that it's 45 degrees towards you.
Yeah, that's okay. That's weird.
It's very weird.
So why? How?
No idea.
Who's wrong? I mean, is this a confident bit of information?
It's moderately confident. So I think probably there's more error in the astroseismic. So this means the pulsation measurements. We don't have as much accuracy on what we can do with there as what we can see, with the planets orbiting.
Yeah, like in this case, no, it's there. We can see the planet. We know where it's going. And as you say, this observation, this most recent visible light observation, is not the only one. That they've been done in the infrared before, and so we've got a lot of detailed data. We know where these planets are and where they're going. We know what the orbit is.
Yeah, well, sort of,
okay,
mostly.
Right.
I mean, there is some uncertainty in that. There's a 10-degree uncertainty in those
we're sounding
orbits.
very confident on that.
Well, yeah. It's okay. So if we go back to the planets, that we remember that these are very, very far away from their host star.
Yeah.
Which means they take a very, very long time to go round.
Well, that's true, actually. That occurred to me before. Is like, it takes how long for Jupiter to go? How long's a year on Jupiter?
About 5 years.
5 Earth years.
Yeah.
And so these are twice as far away. This one's twice as far away as Jupiter.
So these ones, we're talking about tens to hundreds of years for these planets.
And we've only been observing them for, what, at most?
A decade. Yeah.
So that's only a bit of an orbit that you would see there.
Yeah, so there is an uncertainty on how long they take to go round.
Okay,
exactly.
so we might have that a bit wrong, and the models about the pulsations of the star might be a bit wrong, enough for them to overlap and go, oh no, it's all okay. No,
it doesn't look like it at this stage either. So there's two possibilities. Our models might be too simple, and that's, very, very possible. There's a lot of effects you try and take into account, but you can't, account for everything if you don't have the physics to put it into your model, basically.
There's only so much you can do.
Yeah. So we're pretty confident, and it seems that the data are very convincing that we are modelling it pretty accurately. And we are pretty confident that we're getting the direct measurements from the planets pretty well as well. So the uncertainty on those is modest, right? If it's a few degrees. But yeah, so either one of two things means that we've got our models quite wrong and we need to really reassess what's going on here. Or this really is a system where the star's in a different alignment to the planets, which is possible, and there's ways that could happen, but we don't expect it to be very common.
So how could that happen? I mean, give us a quick rundown.
So one possible way would be, for example, for the star to have an interaction with something else. So another star.
Get hit by something or dragged around by something?
Yeah, a
nearby?
binary companion that's no longer there, for example, could have dragged things around. The disk itself might cause an instability and cause the whole star to kind of precess. Now, the disk of material that's in the system is still there, which is really, really cool. So that's another sort of whole group of astrophysicists who are super interested in this star system. Right?
So when you say the disk is still there, you mean there's still a lot of other stuff around this star that hasn't been turned into planets and hasn't been gobbled up or pushed away by the planets. There's still, still a disk of stuff.
There's lots of and there's lots of different parts of that disk which are really interesting. So inside this planet E, the furthest in planet that we know of, there's quite a warm disk of material. It's being heated up by the star itself.
Because you said it's quite a bright, quite a warm sun.
Yeah.
Or quite a warm star.
So that disk, it's about 150 Kelvin. So what's that, like minus 120 degrees? Which sounds cold, but that's warm.
That's warm for
dust.
For dust in space.
Yeah. Because then we compare it to where the planets are. We think that the disk, or the remains of the disk that are still there, is about 45 Kelvin. So getting to minus 230-ish degrees. And then there's this huge disk out beyond where the planets are, which contains an enormous amount of material. And this is kind of similar to the Kuiper belt that we have in our solar system. And the Kuiper belt, which is way, way, way beyond Pluto, throws us in tidbits from the outer solar system every once in a while. Things like comets come from this Kuiper belt. But the Kuiper belt, the amount of matter that's still in that area in this HR 799 system is huge. It's so much that it might even be causing instabilities in the star itself because of its gravitational forces.
So what a great system that not only has it got this really cool, seismological feature that it's pulsing away, but you've got the ability to then measure, see the planets and literally see the planets and see where they're going. And so you can figure out that things seem to be a bit askew. And then you've got these other disks of material. Like this is a gold mine.
It's amazing. And you look at the number of astronomers who are interested in the system, and it's big. So most of the stars that I study, if I go and look up how many people have written a published paper on this star, I'd be lucky to get more than 10 papers on a star that I'm studying, right? This particular one I checked this morning has 824 papers written about it on this system alone.
This is a pretty interesting system.
Yeah.
This has got it all.
So it's got people who are interested in disks. It's got people who are interested in new stars and how they form. People who are interested in pulsations. Of course, a huge number of people who are interested in planets. So it's one of these systems that could be very, very illuminating to tell us about early formations of planets, because we can see multiple examples in a very, very early part of the star's life.
That brings us to the end of another particularly interesting episode of the Syzygy podcast. That story went to all sorts of places I really didn't think it was going to go to. And I could see Emily sitting opposite me here with this look in her eye, which was, you wait, it's coming. That was very cool. Thank you, Emily. Listen, if people want to get in touch with us on the show, you out there in Listener Land, if you've got a question, you've got a comment, you just want to say hi, there are all sorts of ways that you can do that. Emily, tell us about some of them.
Well, if you're on the Tweetyverse, then we love Twitter.
We do.
It's scrolling and never ends. It never ends.
Yeah,
it's so exciting.
You're not selling it to me. It never ends.
You just got to accept the fact you can't read all of the Twitter.
You can't. You're not a Twitter completionist?
No, I don't think so. Unless you count Syzygy, of course.
Well, of course. Yeah.
Then you should read all of Syzygy's posts, and they are found at SyzygyPod. It's SYZYGY.
That's right.
Pod.
That's right. In fact, at SyzygyPod, pretty much anywhere on the interwebs. If you go and find a social media platform and you want to know if we're there, that's where you can try it. We're on the Instagrams sometimes. Facebook, SyzygyPod. Just go and search for us there. That's totally cool. And we have a website, of course. A website where you can find all of the past episodes, all the show notes, and go back and listen to the ones that you've missed in the past.
And we'll put up a little movie of the planets going around the star that were taken in 2010. It's
like this one.
Fantastic.
I'll put that one in the show notes. So that's syzygy.fm, which is the URL of choice for podcasts. But we're going to have to find our way out of this one, so we'll be back again. Emily, you're going away for a while.
I'm going to do some research elsewhere.
Hurrah. So we might take a couple of weeks break, but we will be back with plenty more stories of the cosmos, including, you never know, some interesting stories from what Emily's been up to while she's been away.
And throw us your questions in the meantime.
Yeah, do. We'd love to. We'd love to hear what you want to know. We might even turn it into an entire episode. But until then, we'll catch you in a couple of weeks' time. Bye-bye.
See you later.